Uh, Good afternoon, everyone. I'm just there are participants to be joining right now. In this session, this is the first technical session of this international workshop on technological advances in renewable energy. We have as the chairman of the session, Professor Vinay Dwivedi, and we will be having co-chairman as Professor Sapnil Rai. Then we will be having our invited guest lecturer, Dr. Meet Yan from University of Exeter, United Kingdom, and followed by Dr. Rishi afterwards. Now, as per our chairman is concerned, Dr. Vinay Dwivedi has been doing his schooling from Kendra Vidyalaya and he has done his BSc and MSc from Bundelkhand University. After MSc, he has qualified GET and he completed PhD in biotechnology engineering from Uttar Pradesh Technical University, Lucknow, and performing research work in ICPO and ICMR Institute. He did his research in cancer biology. He has 22 years of teaching and research experience and has published more than 50 research papers in various national and international journals. He has attended more than 25 international conferences and presented papers. He has 7 patents in his name and 4 awards in his credit, and also been a key speaker of more than 20 national and international conferences. Under his able guidance, 3 research scholars have completed their PhD, 1 have submitted, and 3 scholars are continuing. His specialization is nanotechnology, intellectual property rights, plant biology, entrepreneurship, and bioremediation. He is currently working as a director, Amity Institute of Biotechnology, Amity University, Gwalior, Madhya Pradesh. Sir, if you can kindly just talk about us for a few minutes.
Thank you, Vitabrata Malik, and thank you very much. And I'm thankful to the organizer to consider my profile as a chairman for this session. And actually, nowadays, there is scarcity of renewable energy. We have the sources of energy that are exhaustible in nature. So we have to go to develop some renewable energy sources which can help in the sustainable development of the country. So nowadays we are advancing towards the electric vehicles with zero emission, zero carbon emission technologies and various other things. But nowadays technological advances in the renewable energy is very important. And I think after the completion of this workshop, the attendees will be very much aware about the technological advances in renewable energy and how we can cope up with the exhaustible energy and how we can use the renewable energy for the purposes, different purposes. Thank you. And I think I should invite Dr. Meethian for her talk.
Thank you, sir, for your just kind words. Let me introduce Dr. Meetian, and then you can proceed with the his speech. So, Dr. Meetian is presently a senior lecturer in low carbon engineering and an esteemed member of the Global Sustainability Initiative (GSI) community. As a passionate advocate for sustainable energy, her research primarily focuses on hydrogen energy technologies. Currently, she is exploring innovative hydrogen storage media for low carbon combustion systems and sustainable transportation solutions. He has been working on the areas of like environmentally friendly synthesis of nanoporous materials such as porous polymers, porous carbons, and metal organic frameworks or MOFs. Neutron scattering techniques for characterizing hydrogen-based materials, hydrogen storage and transportation solutions, hydrogen and deuterium separation process, and optimization of hydrogen supply chain management. In about Dr. Mi Tian, this in recognition of her outstanding achievements, Dr. Tian was as recently recognized as an EPSRCWS ambassador for women in engineering in 2023. She was named one of the top 50 women in engineering in 2020 and was awarded the EDE and Ravenscroft Prize in 2019. So I just officially welcome Dr. Me for her lecture and delivery. Thank you.
Thank you for the invite and the introduction. May I share the screen? Good. Can you see my screen in present mode?
It is visible.
Yes, yes.
Okay, can you hear me okay?
Yeah.
Okay, good. Hello everyone. Thanks for inviting me to deliver a lecture in engineering port materials for hydrogen storage. So before I talk about the size of hydrogen storage, I'd like to bridge the distance between us. So I'm based in Exeter, United Kingdom, which is located approximately over 5,000 miles away India, and has a 5 hours and 30 minutes time difference. Our university is a hub for pioneering research, especially in fields like the one we're exploring today, renewable energy. So my research focus on hydrogen energy with 4 research themes. The theme 1 is sustainable synthesis and advanced manufacturing. I also have a special expertise in advanced characterization techniques, namely in situ neutron scattering and neutron diffraction and such. Then the application is currently focusing on hydrogen storage and the transportation. I'm also my group is also has expertise in design and optimization of hydrogen supply chain. We also have developed the interactive website highchain.co.uk for education and consultancy purpose. So in today's lecture, I'm going to start giving a brief background of hydrogen energy and why hydrogen matters, and the one of biggest challenges in using hydrogen, hydrogen storage. And finally, I'm going to focusing on 2 of my research projects. I hope after the end of the lecture, we can share some common interests and leading to the Q&A session. So let's first take a look at how we use energy over long term, and we can see global energy consumption is keep increasing, and since 2000 the total increase in energy consumption is about 30%, and by 2019 only if you look at world energy consumption by sources, and we can see only 30% energy was provided by renewable energy sources such as wind and solar, hydropower, etc. And the major proportion of energy we use are based on fossil fuel, carbon-based energy resources, resulting in the increase of carbon emission. It's very clear where we are headed. If we look at the world growth example, we can see the population, world population growth, the energy consumption increases, leading to CO2 emission increase, resulting in global warming. So scientists agreed that a temperature rise of more than 2 degrees Celsius would have an unprecedented impact on our lives. So to help us stay within that 2 degrees Celsius temperature limits, and the carbon emission needs to be reduced by 0 by 2050. It's astounding. So the one of the if we look at the UK's energy, UK's carbon emission by sector, and we can see the energy supply has been the emission from energy supply has been dramatically decreased since 2008. That is because phasing out of coals in the UK. However, if you look at other sectors, transport and business, agriculture, the carbon emissions remain very stable. That's the main challenges for the reduction of carbon emission. To deal with this energy crisis we're experiencing, to deal with the pressure from net zero commitment, the UK government and also globally has put a lot of attention and investment on hydrogen energy since 2019. For example, the 2020, the UK government released a 10-point plan for a green industrial revolution, in which it promised, it set a 5 gigawatt low carbon hydrogen production. And after 2 years, they doubled this target to 10 gigawatt low carbon hydrogen production. And also the government recognized hydrogen energy will play a key role in energy security strategy. So in my view, in the future, hydrogen will play a significant role in the future energy system as a clean fuel, a large-scale renewable energy storage, and it will also significantly contribute to national energy security. So that's the big picture, the background about why we are going to use hydrogen. So there's we can see there's a intention to move away from carbon-based fuel to more renewable resources. And the potential actually for solar power and wind power is enormous, which are actually able to satisfy our global energy needs many times over. Why aren't we making more use of this source of resources? Why are we finding it hard to meet our targets and our commitments to meeting renewable energy generation? Because this renewable energy resources, solar energy, wind power, are inherently intermittent. So we can't rely on sun shining or wind blowing, because we are not able to store the renewably generated electricity at a grid level, large scale. We might only be able to turn the lights on when the sun is shining, which is not very helpful. So hydrogen, how hydrogen energy works, that is actually very easy. So we can hydrogen can be produced from water using by water splitting, using renewably generated energy from solar energy or wind power. And then hydrogen can be used to power your car, your house, whichever need energy to drive. And then hydrogen will be converted into water again. So you can see this is a complete green cycle. Water comes in and out. There's no carbon involved in this cycle. Hydrogen has a great potential to be amazing. However, how to store hydrogen and how to store and distribute hydrogen remain a technical barrier, because hydrogen has extremely low density. It's a very light gas. So the volumetric density is very low. If you look at this energy density table, hydrogen is located here. If you look at gravimetric density, energy per weight, energy per kilogram, we can see hydrogen is excellent. It's 3 times higher than petrol or diesel. However, if you look at volume density, energy per volume, energy per liter here, megajoule per liter here, we can see hydrogen, gaseous hydrogen is neglectable at close to 0. So which means it requires massive volume of hydrogen to be able to provide reasonable energy capacity to travel around. So currently we are store hydrogen in either super high pressure hydrogen tank at 700 atmospheric pressure or liquefied hydrogen tank at -253 degrees Celsius. If you look at this, the left hand photo, that is a hydrogen bus running in London. And you can see there are 4 huge hydrogen storage tanks sitting on top of the bus. Comparing with the size of the private car, you can see directly where the problem is. Both techniques, both methods, either high pressure or cryogenic temperature, are very difficult and expensive to achieve and maintain. They also pose a serious risk issues. Okay, so we want to solidify hydrogen or store hydrogen in solid phase. A solid hydrogen storage not only solves the storage problem, but also predicted to be a near room temperature superconductor. Hydrogen phase can be changed by changing temperature or pressure. If we think about water, that's an easy example. Okay, so if we heat water up to 100 degrees C and we get in air, then we get gaseous water, that is steam. If we cool down water to 0 degree in air, and we got solid water, ice. And so this is very similar process for hydrogen gas. But hydrogen's boiling point and the freezing point are much lower. To solidify hydrogen, we need to either cool down temperature to 14 Kelvin or increase pressure to 400 gigapascal. That's very extreme conditions, are very difficult and expensive. And then we found the nanoporous materials has shown ability to stabilize, to freeze the hydrogen molecules at a much milder condition. Okay, so the porous, the very special feature that the porous materials offer is a large surface area and a very tiny small pores. So as soon as we expose this clean porous surface to gas, this tiny space will absorb, compress, and store gas molecules in its tiny space. So we call this nanoporous materials as molecular sponge. So like sponge absorb water, so our novel molecular sponge can absorb hydrogen. So my job is to gain better understanding on how hydrogen molecules interact with surface, therefore lead to a better design for porous materials. One of the challenges in my research is how to characterize hydrogen. As mentioned, hydrogen is a lightweighted gas, is invisible, and is insensitive to lab-based technology, for example, X-ray diffraction. Therefore, we found the neutron is the best candidate for this job. A neutron is highly sensitive to hydrogen. A neutron beam can deeply penetrate everything, the crossdot, the high pressure sample container, sample itself, and directly probe gas molecules inside the pores. This is so we can see this is a typical inelastic neutron scattering pattern. So this is the neutron, the reactor. So the experimental procedure is like we seal the reactor with the central stick here, and then insert everything into the cross dot underneath of the floor, and then we cool down the system to the target desired temperature, and then we pump hydrogen in. Then we shine the beam through, we collecting the data. At 12 Kelvin, we collected the neutron data, INS data, and we found a sharp peak at 14.7 MeV. And that is a characteristic peak for solid hydrogen, because we only pump the pure hydrogen, solid hydrogen at 12 Kelvin inside the reactor. So we know this is a characteristic peak of INS for solid hydrogen. And then we bring temperature up to 17 Kelvin. And the solid hydrogen melts to liquid hydrogen, liquid phase. And we see this sharp pronounced hydrogen peak disappeared or become a broadening, becomes a big pump. And if we continue increase the pressure, temperature to gaseous temperature beyond 25 Kelvin or 30 Kelvin, and this is the peak, this broadened peak completely flattening, become the flat peak. So which means this red curve, this pronounced peak, is for solid hydrogen. And then we apply our materials following the same procedure in the neutron reactor. And then we, instead of cooling down, we pump the hydrogen in, but instead of cooling down the temperature to 14 Kelvin in order to achieve solid hydrogen, we cool down the temperature at 77 Kelvin. And that is liquid nitrogen temperature, which is much affordable, easier to achieve and maintain, okay? So surprisingly, we see the characteristic peak at 14.7 MeV. That is a characteristic peak for solid hydrogen, but we can, by applying our material, we can achieve that at liquid nitrogen temperature. That is much practical. And we collecting data at different pressure, and we see the intensity of increases, indicating the accumulation of solid like hydrogen increasing with gas pressure increases. Okay. There's an obvious question, does all the porous materials works in this principle? Actually, no. And we tested different materials, and we realized only the porous materials with very tiny small pores, less than 1 nanometer, can solidify hydrogen at this condition. For example, this onion-like carbon with a pore size larger than 1 nanometer, and we don't see this solid hydrogen peak. So which means when the porous materials with a larger pores is too large to accommodate solid state hydrogen, it's not very useful in this case. And we also want to know, we know the pore size plays a key role. We need to keep the pore size smaller than 1 nanometer. And does the pore shape also matters? So to answer this question, we selected 3 different pore shapes. The slit-shaped pores. We can see the few layers carbon sheets represent slit-shaped pores. And we also have the single-wall carbon nanotubes representing cylindrical pores. And also the amorphous, completely amorphous carbon. So from the INS experiments, it shows hydrogen can be confined in different pore shapes as long as the pore size is smaller enough. Okay. we of course we care about the how much hydrogen the material can store. We carried out the high pressure hydrogen adsorption at 77 Kelvin liquid nitrogen temperature, and we found the single wall the single wall carbon nanotubes has slightly lower hydrogen storage capacity. And from the high pressure gas adsorption, we can calculate the hydrogen density inside the materials. And we found that the amorphous carbon has the highest hydrogen density, even that is in solid hydrogen density range, and in single wall carbon nanotubes, which has the least hydrogen density. So to visualize what really happens, we carried out the molecular simulation, and we found, so if you look at these two figures represent two different structures. The golden sphericals are represents hydrogen molecules. The gray bars are carbons. So we can see the in slit pouches in two carbon layers, we at 0.66 nanometer, hydrogen molecules can form highly ordered two-layer structure. That's perfectly fit in this space and cannot move around. On the other hand, in cylindrical pores, from the right-hand figure, and we can see the structure of hydrogen confined are different. They are in a spherical structure with a certain mobility. So the density is much less than the two-layer structure. Okay, that's explain the reason behind the hydrogen storage measurement. So so we achieved the success in this theoretical study, and we know the optimal part structure for hydrogen storage. And based on that, we decided to engineer our material for a new generation hydrogen storage tank. We want to line a linear liner. We want to have a liner inside the high pressure hydrogen storage tank using our porous composite in order to either increase the hydrogen capacity or reduce its pressure. Therefore, we can use more standard material and standard regulator, reduce the cost and improve the safety. So our design criteria for ideal liner material is a good absorbent for hydrogen. It also can be seeded into membranes because most of the current porous materials are in powder form. Powders are very difficult to manage in industry. So we need to, especially we cannot really use powder inside the hydrogen tank with the super high flow rate. Therefore, we need to find some material that can be proceeded into membrane. And it need to be stable and robust. So therefore, we found the polymer of intrinsic macroporosity. So this, you can see, these are the structure, molecular structure of PIM1. So the PIM1 doesn't like the traditional polymer. Traditional polymer has a long linear chain, okay, which can be packed efficiently. So there's no voids. The PIM1 is very special. It's got this rigid, contorted angle here, which cannot be packed efficiently, leaving a lot of voids in its long chain. So that is where hydrogen porosity from. So PIM1 is a macro porous material. Most of the pores less than 1 nanometer, and that is ideal pore size range for hydrogen storage. It can absorb hydrogen about from 0.8 to 1%, which is not really ideal, but okay. It's and the most important property of PIM1 is it can be proceeded into membranes, transparent yellow membranes. So this is a very good starting point. But the porosity is low. Hydrogen storage capacity need to be improved. So in order to improve its hydrogen storage capacity, we doped the PIM1 with different porous fillers. So for example, part1, one of the MOFs, and activated carbon. All those porous fillers has a extremely high surface area, around 3,000 square meter per gram. And also has a small ideal pore size with a pore size less than 1 nanometer, good hydrogen adsorption capacity, and also stable. So doping PIM1 with porous fillers, we can combine the good mechanical properties and processabilities of PIM1 with a good hydrogen storage capacity with porous fillers as a composite. Okay. So these are composite membranes we fabricated. So we dissolve the PIM1 powder granules into DMF, and then we mix with different porous fillers at different concentration. Then we cast it into a powder dish. Then when everything is drying out, and we can see we can lift the freestand robust film up, just like the video shows here. So these are different. The black film are actually the PIM1 activated carbon composite membrane. These two are PIM1 with different porous fillers. And we can see, obviously, with the concentration of fillers increase, the transparency decrease, flexibility decrease. At some point, the membrane cannot hold its physical properties, cannot form the membrane anymore. It's loose, completely lose its mechanical properties. So there's always a balance between the hydrogen storage capacity and mechanical properties. So these are morphologies of part1 MOF and activated carbon. We can see they have different density and particle size. From the cross section of the membranes, we can see the MOFs because the density and the crystal size, they are distributed homogeneously in PIM1 matrix. So then we measured the BT surface area, specific surface area, and that is an indicator, key indicator, how good the material absorption capacity. So we can see the surface area increases, has a linear correlation with the fillers concentration, which follows the rule of mixture. And the majority of pore size is less than or around 1 nanometer. So it's all follows our design. hydrogen capacity is also follows the rule of mixture, is linear relationship with the Filler's fraction. We can see the maximum storage at low pressure is 2 weight%. And then we carried out the high pressure gas adsorption. That's give the full picture of the total storage capacity. So we can see the maximum capacity is this one, which offers around 6 weight% capacity, that already beyond the DOE's target, Department of Energy target, that is about 4.5 weight%. Of course, we carried out the mechanical properties of the composite membrane, how strong it is. So we measured the stress and the strain, and we found the stress strain curve is decreased with the concentration of the fillers, which is not surprising. And the composite membrane thermally stable, higher, they can stand beyond 200 degrees C in air, thermally stable, which is really good. Another problems for membrane for polymer is aging, degradation. A lot of the polymers degrades over time. So to evaluate is aging properties of polymer, we measured, we keep the materials in the same condition over time, and we measured its mechanical property and different properties, and we found the mechanical properties evolve in the first 50 days and then stabilize. Young's modulus doesn't change significantly. Surface area and the low pressure hydrogen uptake keep it stable, which seems unaffected by aging or by time. But the high pressure capacity losses over 100 days and then slow declined. So now we've throughout explored the performance of our PIM1 based composite membranes. We are then consider manufacturing strategy. So a key aspect of this strategy involves shaping the composite to fit our needs. In our case, the goal is to integrate this composite into high pressure hydrogen storage tank. So this application needs a variety of shapes, meaning our manufacturing process must be flexible enough to create complex geometry as required. So that is one method we explored. So we used the free film casting, and then we realized the film casting, the thin film is not sufficient enough to provide enough hydrogen storage capacity. So we need to shape it. And then we use the free casting method to make a monolith. So those are 2 monoliths we are making, which significantly increased the capacity. And we evaluated the mechanical properties of monoliths, which can satisfy the hydrogen storage tank application. And then recently we started to use intelligent manufacturing, namely selective laser sintering, to shape the composite. We use the in-situ synthesis, which means we under ex-situ synthesis. So this is the Snow White selective laser sintering we are using. So basically, we in in-situ synthesis, we synthesized the composite first and then put it in the Snow White equipment and print it out. And then, of course, you can control the shape, whatever shape you want. In in-situ synthesis, we print the shape out using polymer, and then we grow the morphs on the synthesized film. It's not only film, but because it's a bit simple, but it also can be different shapes, different cages we are testing. So this is a fascinating area and really bridge the lab technology and industry applications. So which brings to us to the end of my talk. So just quickly summarize the new generation hydrogen storage tank. So I hope I convince you hydrogen energy is going to play a role in new future energy system, and hydrogen storage has key challenges in the whole hydrogen energy applications. Our research has demonstrated a strategy to solve the low density problem of hydrogen storage and transportation. We are we are carrying out from theory to engineering level. And these findings are a first step towards the production of truly useful material to really solve the real world problems. And finally, I'd like to take this opportunity to acknowledge all my collaborators and the founders for their finance support. Thank you very much.
Thank you, ma'am. Thanks for your research that you have shared with us. And I think nowadays, actually, the hydrogen can play a very key and pivotal role, basically, as a renewable source of energy. But the main thing is that because it's a very costly affair to separate the hydrogen from the water or from any other source. So if we can separate the hydrogen in an economical manner, I think this will be a great discovery, basically, and it can be helpful can be used as a renewable source of energy.
I agree. Yes. So it's expensive. Hydrogen is in general a very expensive technology. So that's the challenges we need to overcome. And the cost about hydrogen is related, well, determined by the electricity, basically. So nowadays we see in the UK, in Europe, we see a negative price for electricity. And also, if we look at the wind turbine, they are not always spinning. A lot of times they are not spinning, they are not working, because at the off-peak time, energy usage off-peak time, they cannot accommodate that electricity. So they have to. We don't have choice to store those surplus energy, but switch the wind turbine off.
Yeah.
That is a big waste. I think the for the role of hydrogen, one of the roles hydrogen is going to play is to accommodate those surplus electricity from intermittent renewable energy resources.
And secondly, I would like to ask one more question.
Yes,
That
please.
as you are working with the engineering material for hydrogen storage, so actually what can be the maximum capacity in which we can store the hydrogen?
That's some, hydrogen is a gas.
Yeah.
So it's depends on conditions, the pressure and the temperature you can offer.
Actually, I would like to know about the area that is specifically required, because
So you
if a
can
huge
see,
area is required.
I think the maximum, if we without considering the cost, without considering anything, just the highest, we can consider the density of solid hydrogen, which is 80 megajoule per kilogram. No, 80 kilogram per cubic meter. So that is the maximum density hydrogen can achieve.
And secondly, what about the transportation? Because if we want to transfer that particular hydrogen from one place to another, so what is the most feasible way to transfer?
Oh, there's many different ways. People are still testing. One is using blending using the pipelines.
Okay.
So currently, in the UK, hydrogen has been it is under testing. So blending with natural gas, use it for heating in household. So it can be blended with the natural gas and transferred using pipelines, natural gas pipelines. That's one method. And the most commonly is to fill in the hydrogen tank delivered by a truck, which is called hydrogen trailer.
Okay.
Mm.
And secondly, can we use some nanoparticles for the storing of hydrogen?
Yeah, nanotechnology also has been explored in this area. Well, it mainly depends on material you are going to use, which use different technology. For example, for metal hydrides, and then we generally need to bring the nano hydrides to metal hydrides to nano size.
Right.
That is nanoparticles, but it's still not ideal because the activation and the hydrogen charging and discharging temperature is still high, which requires catalysts to speed up the reaction. And for porous materials, it doesn't, the particle size are not really critical, but pore size and surface area. So
No,
that
so
depends on
actually,
different temperature.
during the construction of the specific material for hydrogen storage, if we mix the nanoparticles, because it enhances the surface area to store the hydrogen. So it can be mixed, that I'm saying, whether this nanoparticles can be mixed with the different type of materials so that it may enhance the surface area of the container or anything in which we can store this hydrogen.
So again, that depends on different materials. For the MOFs, for example, or most porous materials, we want to keep the good crystallinity and reduce the size. So my
Yes.
damage is porous structure because especially some MOFs are not very stable. When you break down, the porous structure collapse. So the voice collapse, there's no, is actually reduce the surface area. But actually, but sometimes bringing the particles down to nano size can generate active size, which sometimes also benefits hydrogen storage. So it depends on different storage mechanism and the different storage material.
And secondly, can we use such type of material in which the hydrogen can be adsorbed on the surface, and after transportation, it can be detached from the surface and can be utilized for some other purpose?
Oh, this is all reversible.
Yeah.
So you can charge and discharge multi times.
Yes.
Because this is a physical desorption driven by 1 watt force, so it's completely reversible.
Okay, thank you, ma'am.
Thank you.
Yeah.
Is any questions from the audience?
Yeah. Any question from the audience?
Okay.
Okay.
If anyone has any question, you can ask. If anybody has any query, you can ask here.
Okay. So if not, I think thank you very much for inviting me to deliver the talk. Enjoy the rest of the workshop.
Thank you, ma'am. Thank you.
Bye.
Thanks for this valuable talk. Thank you very much.
दो एक दिन में बताऊंगा.
Sorry?
Any participant want to ask any question, you can ask here. Okay. Okay, sir. So we'll be welcoming our next guest speaker. Will be Dr. Rishi. He'll be joining soon, just within a few minutes.
Sure.
So participants are requested to be here, and we'll be starting. We'll be continuing in this session.
Dr. Malik, has she left?
Dr. Me has left.
Sir,
Okay.
we are waiting for our next speaker, Dr. Rishi.
That is okay. Actually, I was not having the right to speak. I was asking. I was about to ask related to a safety issue, but no issue. We'll discuss later.
Gas turbines. Geothermal has found a new way that is we can
Dr. Malik, have you called Dr. Rishi?
He will be joining soon. Actually, he has some urgent meeting, so that's why his speech is from 3, so he'll be joining in 5 minutes.
Okay, no issue.
Uh, Meanwhile, I will ask Professor Sapnil Rai to speak on this theme for this few minutes to address the same.
I'll speak after in the end. Malik, Dr. Malik, I'll speak in the end. No issue.
आ गया होना चल रहा की करा ताला नहीं बच्ची
Hello, am I audible?
Yes, sir, you are audible.
So, Dr. Sharma, I think he is joined. Dr. Sharma,
Hello.
hello. How are you, sir? Good afternoon.
Yeah, good afternoon. I'm fine.
So now,
Just uh, can you give me 1 minute more
no,
time,
no issue, sir.
please?
Yes.
I'll be back in a minute.
No issue. Very good.
Welcome, sir.
Very good afternoon.
Yeah, good afternoon.
So we'll
Sorry
be
for
starting.
the delay.
Yes, sir. Yeah. I welcome Dr. Rishi Sharma to this session as an invited speaker for the technical session one, and all the participants kindly mute yourself if you are on. So we'll be starting this second invited lecture. Let me first introduce Dr. Rishi Sharma. Dr. Rishi Sharma is currently working as a principal scientist in Semiconductor Sensors and Microsystems Group at CSIR CEERI Pilani. He is currently working on the design and development of MEMS based microsensors for chemical and biochemical sensors. Apart from this, he is also working as assistant professor in SIR in CEERI Pilani as Academy of Scientific and Innovative Research, Ghaziabad, Uttar Pradesh. He is also an adjunct faculty at IIST Shibpur. Before joining CSIR CERI, Pilani works as an assistant professor in Amit University, Noida from October 2009 to April 2010. He received his MSc in Electronics and PhD in Electronics from Jivaji University, Gwalior. He has obtained a research fellowship from the University Grants Commission, New Delhi, and from DRDO, India. During in PhDs, he worked on the development of organic materials-based detection systems for toxic agents. He has published 70 research papers in international and national journals and conferences. Dr. Sharma has also co-authored one book chapter. He is a life member of the Instrument Society of India and member of IEEE USA. I welcome in this session to Dr. Sharma. You can share your presentation for the audience. Thank you.
My presentation is visible.
Yes, sir, it's visible.
Sir, it is visible when you go for slideshow mode. So
Okay, just a minute. Now is it visible in the
Yes,
slideshow mode?
okay, okay, yes.
Yeah, it's
So the
visible, sir.
slides are changing? Okay.
Yeah, it's moving, sir.
Sir, before proceeding, sorry, I'm entering in between. Before proceeding, I want to tell you that we are having Professor Dr. Vinay Dwivedi, the head of the Institute of Amity Institute of Biotechnology, as a chairman of this session. And uh, that's just want to inform you. So, Dr. Dwivedi.
Good afternoon, Dr. Rishi. This is Dr. Vinay Dwivedi this side. And welcome, sir.
Yeah, so nice to see you, and thanks for the invitation for the workshop. With these words, let me start my brief
Sure, sir.
presentation.
Please continue, sir.
So, my topic of presentation is broadly, I tried to bring out some of our research. Is my sound is clear?
Fine. Fine.
Okay, so yeah, okay. So I try to bring out some of the research to the topic, which is related to the renewable energy. And outline of my presentation is about the introduction, about the energy harvesting applications, and why there is a need of energy harvesting. Then the research motivation, followed by different techniques. I'm touching few techniques and not going in detail. And then some of our works, which we did by using graphene-based materials for energy harvesting applications, and development of other materials which are relevant these days for the energy harvesting applications. I would like to start with the picture of Professor Chetan Singh Solanki. He is currently on lean, and he's a professor at IIT Bombay. So he has established one organization which is working for the creating awareness among the people about the energy harvesting area. And so he is traveling across the India, and he's known as one of the stalwart. And recently, IIT Bombay has also awarded for his contribution, and the CSIR also has signed a kind of MOU with him for the awareness. And recently, I have also attended the classes of Professor Chetan Singh Solanki. So, what he has highlighted that with the global warming, there are a lot of natural calamities and natural difficulties may come up. So globally, it is working that how to reduce the rise of global temperature, and this can be done only by usages of alternative energy sources, and so I mean, by using those alternative energy sources, we can control the rise of global temperature within 2 degrees Celsius. Because if the rise of that temperature will be high, then the glacier and other will going to melt, and it will damage the ecosystem of the entire world, and this will going to affect the entire humanity. So I also advise, if the students are listening, uh, to follow Professor Chetan Singh Solanki and listen his videos to get themselves aware about the how to save energy, and uh, mere losses of uh, energy cost lot of thing, and it will also affect the global temperature. So he has just tried to connect uh, like simple usages of air condition systems in house, or the electricity at home, how if we misuse, how the losses of energy happens. So these are some of the well-known technique through which the energy can be harvested by utilizing natural processes like solar energy. We all know about the photovoltaic cells, and government of India also has initiated a lot of schemes for the utilization of these photovoltaic cell based lightning system for the houses. And the energy can be also harvested through wind energy, hydroelectric power, and biomass energy. Hydrogen energy is also one of the upcoming area, and a lot of research is going on in India also, the utilization of hydrogen fuel for the vehicles. And uh, the tidal energy, or the nuclear energy, or the small modular reactors, which can also cater the possible uh, waste materials of nuclear waste, you can say. So by utilizing those modular reactors, the energy can be harvested in a such a way that the losses can be uh, environmental losses can be minimized. Then the ocean thermal energy conversion, which is also uh, harvested through the difference of temperature at the sea upper level and the bottom level. So these are all the various energy harvesting methodologies through which one can utilize the naturally available resources to generate electricity without affecting environment in a broad sense. So this is like solar power, the India's the largest solar uh, power plant, which is floating on uh, uh, the area in the Telangana area, one lake, where they have installed the highest 100 megawatt solar power project in India. So this is just an example how this solar power can be utilized. And another area which Government of India also initiated, and we are also working on the hydrogen fuel generation. And this is the various pathways uh, through which the hydrogen energy can be produced by fossil fuels or the renewable sources. One is like by water splitting, or electrolysis, or PEC, or thermochemical technique. And other is like biological processes through which the hydrogen can be extracted by biochemical processes. Another is like by fossil fuels. So these are like pathways which through which one can produce hydrogen and utilize this for energy applications. So this is one example of the initiative taken up at CSIR, and CSIR labs. One is located in Pune, and another is in Sikri, Karaikudi. They have jointly working for the development of indigenous hydrogen fuel cell bus, and it was launched in 2021 at Pune by our former DG, Dr. Mashelkar.
I think there is a network issue. उनका वहाँ नेटवर्क का इशू हो रहा है maybe there is some network issue. Please, participants are requested to wait for.
Now the screen is visible.
Yes, sir. Yes, sir. It's visible. You can continue, sir.
So is there some network issue which you're not receiving at your end, my slides?
Sir, yes, previously it was for some few seconds. There was a network issue.
Okay, so let me just stop my video. Maybe like it will give bandwidth to the network. So yeah.
Yes, sir.
So this is I previously discussed about the hydrogen fuel cell bus, which was jointly developed by CSIR, SICRI, and CSIR laboratory located in Pune. This is one example of the solar spectrum. As you can see that the solar spectrum consists of band set from 250 nanometer to 2500 nanometer, and it is consists of UV visible and IR radiations. So a lot of research is also going on by utilizing the entire spectrum, how the efficiency of the photovoltaic cells can be increased. So I'm not going to touch the entire set of research. I am just giving some examples. Like organic solar cell based research is also going on, silicon based solar cell. The basic motivation is to increase the efficiencies of the solar cells. Similarly, as you can see on the right side of the slide, it is consists of the diagram which shows that some of the spectrum of the light and sunlight uh, used for say 58% is used for the generation of the photovoltaics, and rest 42% is drain out in the form of say heat. So it is not utilized. So techniques like thermoelectric based energy harvesting methodology can be used for the utilization of the rest 42%. So in a way, we have to work, and a lot of students should also focus uh, research in this area, that how the efficiencies of the photovoltaic cells can be increased, and also utilizing the entire band of the solar spectrum wherever it is possible. Thermoelectric is one of the methodology which is useful to harvest energy. It is also, a lot of research is going on. It is basically based on the Seebeck and Peltier's effect, where the two materials are joined and the temperature difference is utilized for the generation of energy. So by utilization of the microfabrication techniques, one can develop a small energy harvesting system utilizing the thermoelectric energy. Then other is the EDLC and supercapacitors is also one of the area, because the research for the energy harvesting is also important for uh, um devices and systems which are implanted on the body or the wearable sensors. So EDLC kind of sensors, which is the base for the development of the supercapacitors, which are having importance by transferring more power uh, at the time of need. So supercapacitors, they have they're different from the normal batteries in the sense that when we require more power, the high power can be easily transferred with the use of supercapacitors. So development of micro supercapacitors uh, is also one of the important area, and we have also worked for the development of micro supercapacitors by utilization of different materials, including carbon-based materials. So the basic challenge for the supercapacitors is to increase the power density and as well as the uh, power efficiency. So overall, eh, we have to design a system or a material so that the power density can be increased, so that we can increase the uh, voltage as well as the power storage capacity. So there are also like fuel cells which uses the energy storage. They have low power density but higher energy density. Whereas the EDLC, which is nothing but it is electric double layer capacitors. So they are used for supercapacitors. So this is like some of the materials which are useful for the supercapacitors. Basically, supercapacitors can be classified into electrochemical double layer capacitors and pseudo capacitors. Pseudo capacitors are nothing but it is the combination of, you can say, the polymers and metals, so that the both type of reactions, Faradic and the electrolytic uh, PLC based, can be done in a together way. So for the say EDLCs, the activated carbon or carbon fiber or graphene based materials are used, and the pseudo capacitors, we can have the combination of the polymers like polyaniline, polypyrrole, and PEDO, PSS. And a lot of work is going on in the manganese oxide and rhenium based oxide for the pseudo capacitors. And other asymmetric hybrid supercapacitors are also used, where the two methods are combined together, and where the electrolytes are also used, and they are basically ionic based, also some ionic liquid based electrolytes, they are also used. So this is a broad classification of supercapacitors. So this is like history of advances of supercapacitors, that how the EDLC it can be developed in the two form. One is in the full cell mode and one is in the half cell mode, where the planar structures are developed, and on the top of that the electrolytes, and followed by encapsulation. Here the uh, it is a sort of hybrid structure where the separator is used, and on both the sides the electrodes were developed. So in this case, the packaging of these type of electrolytes supercapacitors is very challenging. So like from EDLC to pseudo capacitor and pseudo capacitor to hybrid capacitor. So this is like journey and the application, as I said, that for the micro storage applications, like where lightweight supercapacitors are used, it is useful for that matter. On the right side, a lot of applications are being highlighted, like micro capacitor, wearable devices, then self-powered supercapacitors can also be developed by doing integration with other methods like solar powered. With the help of solar power, one can charge supercapacitor also. Then the transparent type supercapacitors, where the different materials are used in such a way that directly the solar powered method can be used for directly charging it. Then the portable patch type and the bendable type of supercapacitors are used, and a lot of work is going on in this area. Yes, work we did around 2 to 3 years back, where we have used graphene as one of the material, and during the development, uh, we are also trying to enhance the energy storage capacity of the micro supercapacitor. For that, we have used graphene, and along with the polypyrrole as one of the material, as a binding material. So what we could able to, by utilizing the two reactions at the same time, to say that we have used the ammonium persulfate and H2SO4 simultaneously. We have developed the method for the generation of the graphene nanoscrolls. Graphene nanoscrolls are different from that of the CNT, carbon nanotube, in a way that when we prepare graphene by the exfoliation technique from the graphite, by utilization of Hammer's method, there are various methods through which the graphene can be developed from the graphite. Electrochemical techniques are also there. So we have used the Hammer's method to generate the graphene, and then we have simultaneously polymerized polypyrrole along with the graphene. And with the utilization of different oxidants along with the acidic medium, we have generated the graphene nanoscrolls. So graphene nanoscrolls have capability for the generation of the porous structure, which is very well important for the easy electron transmission through the membrane for higher energy storage. On the left hand side, you can see that this is the TAM image of graphene nanoscroll. If you just see that the graphene carbon particles are visible on the left side of the screen. On the right side, it also shows a lot of scrolls they are formed along with the polypyrrole. This image on the right side, you can see that typical structure of graphene nanoscroll, where if you see that the small gaps shows that the presence of carbon particles. Through TAM and HREM, we can able to also evaluate the distance between carbon-carbon atoms to confirm the graphene nanoscroll. So we have checked it, and on the left hand side, we can see that it is very porous structure, and the graphene nanoscrolls are embedded into this polymer matrix. So this material is then used for the supercapacitor. And then we have done the cyclic stability test of these materials. The good part of this material is that it can be fabricated directly on the microstructures if we dipped it in the solution, and then followed by the electrolyte encapsulation. So we have tested it in the two electrode method, where on one substrate the this capacitor is formed, EDLC capacitor is formed, and it is tested in presence of sulfuric acid. And we have tested cyclic stability, and the specific capacitance was quite good. Around it is more than 600 farad per gram. And further, we have worked for the miniaturized structure, which has further increased the specific capacitance of that material. Recently, a lot of work is going on with the since the topic of the conference is on the energy harvesting applications, as and also we know that lot of EV based battery based vehicles, they are coming up in country. So lot of places we need the workstations to charge those batteries for cars or for vehicle like Ola scooters and so on. So those chargers, they required to handle the high energy. So for the utilization of, for the generation of those power devices, the wide bandgap semiconductor materials, they are coming up, and lot of research, and the government of India has initiated program for the development of wide bandgap based semiconductors for these applications. We are also like working on some of the areas which is utilizing the silicon carbide, gallium nitride, or diamond based materials, which are high band gap materials, and they have better thermal conductivity and stability, and they have capability of utilizing at high power. So for higher power applications, since the lot of need is coming up for the battery based transport system, we need to have development of these devices. Along with this, we have also worked on the development of aluminum nitride or titanium nitride. Aluminum nitride is, and these materials, there also comes under the category of wide bandgap materials. So I am just presenting, since the material is useful for energy harvesting applications. So we have developed that material. So I am highlighting the applications of those materials which we have also worked. I'm just going to briefly touch on these slides. It is more to do with the FET based sensors which we have developed at CD. In this, which is ion sensitive field effect transistor, which we have used for the pH sensing applications. In this, we have used different configurations for these all fat structures, because I'm not touching it in detail in the sense that since it is not directly correlated to the conference theme, but we have utilized these materials for the pH sensing applications using ion sensitive field effect transistor, which is nothing but it is the equivalent to that of a MOSFET, where the gate of top gate of the MOSFET is replaced by the thin film, and and it is used for the testing of different ionic solutions and also for biosensing applications. So this is an example of ion selective electrodes. So ion sensitive field effect transistor is, one can say, that is equivalent to that of a ion selective electrode, but it is the electronics version to it, because ion selective electrode, they uses the glass based cell. So these similarly materials which we have developed, we have used for biosensing applications also. So I'm not touching them. These are some of the designs which we have used for the fabrication, meander shape, meander shape, and as well as the planar one-dimensional structure. And this is the basic lithography method which we have used to realize it. This is the mask layout of the SFAT chip. On the right side, it is the gate of the SFAT. And this is, we have worked for the reactive sputtering method to fabricate the titanium nitride and aluminum nitride film. These films are used now for energy harvesting applications, including utilizing it for uh, energy piezoelectric based energy harvesting systems, as well as for the supercapacitor based electrodes. So this is just the SFAT, and this is the deposition of this titanium nitride and aluminum nitride on the silicon wafer. This is the packaging and of the SFAT, and this is like the pH testing of ion sensitive field effect transistor. So this is the different material, as I said, that we have developed aluminum nitride and as well as titanium nitride. So we have simulated and also fabricated and tested these all materials for the pH sensing applications, where we have seen that the aluminum nitride and tantalum pentoxide materials, they have better stability for the entire pH range. And similarly, these materials are useful for the energy harvesting applications. So this is, we have tested titanium nitride based materials. These are the rugged material, and they are very hard materials. So they are very stable in the harsh environment. And these are used as a electrode material even for the hydrogen based applications and hydrogen storage applications. And these are also useful for the supercapacitor development, where TIN is one of the electrode material. So in that way, this material development is useful. We have tested it for the pH, and the work is going on for the energy harvesting applications. So this is like the stability of titanium nitride. We have tested for the pH 4, 7, and 10 in a repeated way, and we have found that this film is very stable. So the development of titanium nitride is very successful. We have tested the drift analysis of TIN based SFAT also. And similarly, the extended gate field effect transistor was replicated by utilizing the same material. So this is the pH sensing setup for those electrodes. And this is again the testing of EGFET by utilizing of titanium nitride gate. And this, I said that since this material is very stable, so we have tested for so many days about the stability of that material at different pH levels. And so we got the repeatable results. So this is like drift analysis of titanium nitride based EGFET for 4, 7, and 10. and the drift was quite within limit, which can be catered up by the suitable electronic circuit. So in a conclusion, I have touched briefly about some of the existing applications and energy storage methods for this, and utilizing titanium nitride and aluminum nitride based materials for the energy harvesting applications. So with this, I would like to acknowledge the support from our director at Siri Pilani and all the scientific and technical members who have contributed in this work, and all who have contributed in one way or the other. So these are the references. So, thank you. Is there any question?
Thank you, sir. Participants, if you have any query, you can ask. Yes, Sandhya Agarwal, you can ask. Please.
IT, please give the rights to speak. Sandhya.
Good afternoon, sir.
Good afternoon. Good afternoon. Please.
Yeah.
I have a question regarding you talk about the cells. Sir, which type of cell, like nuclear cells? Can you explain a little bit?
Cell regarding fuel cell.
Yes, the solar panel cell which you talk about it, the nuclear cell.
No, it is not the nuclear cell. I talked about the fuel cell. Fuel cell is also one of the energy generation applications, and I talked about the basically fuel cell,
Sure,
hydrogen
sir.
fuel cell, which is used for the generation of hydrogen, like electrode based some biological reaction. If you see with that biological application, the hydrogen can be generated. So that type of cell where the electrodes are used and some kind of reaction takes place and the hydrogen is generated and you extract that hydrogen. That type of cell I was talking, not like nuclear cell.
Sir, I would like to ask one thing.
Yeah.
Yes, actually, as we know that hydrogen fuel is the need of future, but is it possible to store the hydrogen as a fuel and it can be transported from one place to another?
As far as I mean, the current, I mean, I have not deeply touched this subject, but what I have seen is that they have extracted hydrogen and at the same time utilizing it in a system like the hydrogen fuel cell based bus, which they have used. So they are
Actually, they
generating
have made the system in such a way that you can just generate and utilize the particular hydrogen fuel in the particular thing. Yeah.
Yes, correct. So there is like a arrangement where the generation of the fuel is taking place and at the same time the consumption is also going on. Any other question?
Sir, can you like put some light on that about the safety issue with the hydrogen energy? Because it is
actually,
of the
yes,
safety.
Yeah, a lot of safety issues is there because this is very dangerous also in terms of its energy. And like in our group, one scientist is working on for the detection of the leakage of hydrogen. So utilizing those sensors that if any leak occurs, then the safety measures can be taken up at the same time.
And sir, any
attachment of those type of sensors and what type of method is one going to use for the generation of hydrogen, that also depends. So if say we are using electrochemical based where water splitting is used, so definitely I mean safety can be done by utilizing those sensors. And then the encapsulation and other which should be done in the leak proof containers. That is how it can be done.
Okay. Thank you.
And secondly, the generation can be controlled, means whether what the amount we want to, we can generate only that much amount of hydrogen fuel.
Yeah, it is possible. As far as I know, I mean it is possible in a controlled way, in a controlled environment. I mean, I'm not like directly connected too much to this hydrogen generation. So, I mean, I only highlighted that these type of research is going on, but definitely as far as the safety protocols are concerned, I was there where the sensor, we are working on the hydrogen leak detection systems. So this come up with the NCL laboratory where they required the sensor so that the hydrogen leak can be checked at the same time. So that way, this is one area which I touched.
Sir, another is graphene. You talked about the graphene. Graphene nowadays is is very popular. It is being used everywhere. So how
Okay.
is it different? Like if I term its efficiency, how its efficiency is better we can use in your this area in supercapacitor and other things.
Basically, it's more to do with the surface area.
Okay.
We can increase the surface area. As I said that the graphene nanoscrolls, it is basically the scrolling of a larger graphene sheet. So in a way, when the paper is rolled, so when it is rolled in a circle, CNT is like fused, like a circle, but scroll will be open up like this. So a lot of material can also be incorporated within those layers.
Okay.
And it at the same time it is porous. So and since it is scrolled, so a bigger sheet is scrolled in this form, double layered form. So the more surface area will be there in comparison to that of a CNT. So one can adopt the method through which the surface area can be increased. For that matter, like a lot of people are working by utilizing the CNT zipping.
Okay.
CNT का zip भी कर सकते हैं.
about descriptor.
So the zipping of CNT can.
You said, right? Yeah.
Pardon?
Vinay, unmute yourself. You are saying something?
No, I'm not saying.
No, sir, not you. Another Vinay Vikram Singh is there.
Okay.
Not you, sir. Vinay Vikram? No, sir. Okay, sir. Continue, please. I think.
Yeah, so the actually unzipping of CNT can be done so that the nano ribbon type of graphene sheets can be generated, and then we can utilize that along with other sensing materials like polymers and manganese oxide and ruthenium oxide and other these kind of materials can be simultaneously utilized to increase overall surface area. And the porosity of material is important because the easy ion transport should also happen for the efficient generation and the transfer of power from the storage to the required machine. So that efficient transfer should also happen. So the porosity is equally important.
Okay. Thank you so
Sir,
much, sir.
as hydrogen fuel is one of the way to generate hydrogen. So is there any other way with the help of which we can generate hydrogen that can be utilized as a fuel other than hydrogen?
Like
fuel cell?
I have to check. I don't remember. I don't able to recapitulate at this point of time.
Who's using this mask?
It can be
Yeah.
generated.
Okay, you are using the mask. And do you know that the speed that you've got is impacting the efficiency of the respirator, or you're not familiar with it?
Slightly, that may be affecting certain frequencies, but again, in the second time, if you are inhaling acid, so that is more dangerous than affecting our respirators.
Yeah, but
So,
what I'm saying is,
Yeah.
if you've got a beard and you've got a mask, it's very likely you're still inhaling the acid.
that may be a little bit amount. While beyond that,
Mr. Vinay. I think he is in some other other discussion and wrongly he has unmuted. Okay. Thank you so much, sir. You have given
Okay.
wonderful insight about this capacitors and other things. And I expect that all of our participants get benefited with this. Dr. Malik, continue with the session.
Yes, just thank you, sir, for covering the broad spectrum about this your lecture. Now I will ask Professor Swapnil Rai, the co-chairman of this session, to just give a concluding remarks based on the session's overall deliberation.
Before I speak, I request Dr. Vinay Devedi, the chairman, to
Yes,
give
sir. Yes, yes,
insights
yes.
about both the lectures.
Thank you, Dr. Roy, and thank you, Rishi sir, for such a wonderful talk. I think definitely the students and the participants will get benefit that nowadays, because as you know that in renewable energy is the energy requirement of the future, because most of the energy sources are exhaustible in nature. So we have to go for the alternate source of energy. And I think fuel cell and hydrogen fuel is one of the best alternative for that. Thank you, Rishi sir, for your wonderful lecture. Thank you very much.
Thank you.
Okay, thank you, Vinay sir. So the second session of the workshop, we were having two great personalities in our lecture. One is Dr. Meet Yang from the University of Exeter, and she talked about the hydrogen energy and hydrogen energy technologies and various aspects of the hydrogen energy technologies, including the sustainable synthesis and advanced manufacturing, neutron techniques, hydrogen supply chain, and hydrogen storage and transportation. Also emphasize the role of hydrogen energy along with the limitations. So from her lecture, all the participants got benefited, and queries were there, and they got motivated with that lecture. Then another lecture of Dr. Rishi Sharma, who is a principal scientist at the Siri Pilani, delivered a very wonderful talk on the capacitors and use of different types of materials in enhancing the capacity or enhancing the efficiency of the capacitors, pseudo capacitors. And also in the end, the question answer round, he has given a wonderful explanations about the hydrogen, about the question related to the hydrogen energy asked by the chairman sir, as well as I also asked about the graphene, and he has explained well. So with this, we have completed, and we are coming to the end of this second session of this workshop. I expect, is there any query from the student side or from the participant side they can ask, or I think we may end this session with the permission of the chairs.
Sure, sir. And thank you, Rishi sir, once again for the wonderful lecture. Thank you very much, sir.
Okay, thank you.
Thank you, sir.
IT, please end this. Malik, we should end now.
Yes, yes.
So who is on the IT side, please end this.